So this chapter is on temperature and heat, and we'll start with temperature. You're probably familiar with the temperature scale, so if I give you and I give you the Celsius scale and the Fahrenheit scale, and maybe the Kelvin scale. So this is 0, this is 32, and this is like 273. I think it's 0.15, but it doesn't matter. This is, of course, at atmospheric pressure. And then for boiling, it's 100 degrees. I suppose it should be 0 degrees, 212 degrees, and this is 373. Notice that the Kelvin scale and the Celsius scale are scaled the same. That is to say, a Kelvin and a Celsius degree are the same. There's 100 between boiling and boiling water and freezing water in both cases. And so we can write these things a few ways. We can say, like, the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32 degrees. And we can say, if we reverse that, we can say the temperature in Celsius is equal to the temperature in Fahrenheit minus 32 degrees times 5/9. This is just an algebraic rearrangement of that one. And then we can say the temperature in Kelvin is equal to the temperature in Celsius plus 273. And if you need to go from Fahrenheit to Celsius, to Kelvin, you can rearrange those and do that. And so I can just do an example. If for 100 degrees Celsius to temperature in Fahrenheit, I would say temperature in Fahrenheit, the temperature in Fahrenheit is equal to 9/5 times 100 degrees plus 32 degrees, which is equal to 180 degrees plus 32 degrees, which is equal to 212 degrees. So that's the Fahrenheit temperature that corresponds to 100 degrees Celsius. So you can do as many of those as you want for practice. So let's talk about thermal expansion. So if you take an object and heat it, these are little flames, right? It expands. It can be a piece of wood or a piece of metal or something like that. The reason it expands because when atoms gain thermal energy, they vibrate more, and that causes the object to expand. And so it turns out that the rate of expansion the expansion with respect to temperature, the change in length I would write it this way, is proportional to the length. This is dl dt is the change in length with respect to a change in temperature is proportional to how long it is. Hopefully this makes common sense, sort of. How much expansion you get depends on how long the object. An object that's really short isn't going to have much expansion. An object that's really long is going to have more expansion. And so, assuming they're made out of the same material, and so you can always change a proportionality into an equal sign by just inserting a constant. So we write it this way: the change in length of an object with respect to a temperature is equal to alpha. So that's a proportional sign for math, and that's a Greek letter alpha. Don't get those mixed up. L. And so this is the proportionality relationship. This is the relationship between the change in length with respect to temperature is proportional to the length, right, to how long the object was in the first place. And so alpha is called the coefficient of thermal expansion. So let me just give you an example. For the Golden Gate Bridge, it's 2 words. The length is 1,275 meters. Between winter and summer, temperature change is delta T equals 55 degrees Celsius. In other words, T winter is like minus 15 degrees, and T summer is equal to 40 degrees. And so we want to know the length change, right? And so we had dl dt is equal to alpha L. And so that says that dl is equal to alpha L dt. And so we can approximate this and just call this the change in length. The dl is equal to alpha L times the change in temperature. And we know all these if we assume that the bridge is made of steel. So alpha for steel is 12 times 10 to the minus 6th per degree Celsius. Can you see that on there? Right. And so that means the length change is equal to 12 times 10 to the minus 6th per degree C times 1,275 meters times 55 degrees C. And so that comes out to 0.84 meters. That's actually a long bit. That's bigger than this, right? And that expansion has to take place in the bridge. Now the bridge probably has sections that are shorter than 1275, but a lot of expansion has to take place between the winter and the summer on the spans in the bridge, and the bridge has to be designed to account for that, to allow for that. Often, even on overpasses, you'll see things that look like this, like intertwining fingers on the road between the winter and the summer. In the winter they look like this, and in the summer they look like this, to allow the span of the bridge to expand into the supports.